this is our Q. Right? So the web controls the direction. So the shear flow, the flow of the shear stress has to be coming down. So for that to happen, this has to go left and right. Excuse me. So the important thing to remember is the would distribute the shearing stress, right? Shearing stresses. The fastener transmit the shearing stress, what shear, okay, from, okay, so it's going to be from the, okay, it's going to start from the, okay, from the flange to the webs, right? So it's going to distribute on the what? Flange first. That is why you only calculate the flange. Remember, all these are separate parts, okay? So you only take the first moment of area at the flange, okay? Right, so we know that Q, first moment of area of the flange, will be equal to width times depth multiplied by y bar, okay? So what we know that the neutral axis, sorry, the centroid, I won't call it neutral axis. The centroid, right, is 60 millimeters. Right. So I'm just eyeballing this, okay? So from the top coming down, this is 60 millimeters. Okay, we calculate that. Okay. So from here, we know that the width is 200. The depth is 40. The y bar with the centroid is 60 minus by 40 divided by 2. Okay. So it's equal to 60 minus 20 times 40 times by 200. So it's equal to 320 times 10 to the power 3 millimeter cube, or 320 times 10 to the power 6 millimeter cube. Okay. So now more or less we have everything already. Okay. So now we know we just need to substitute into this formula over here. Okay. So I'm going to copy. All right. And paste. All right. So all we need to do is put 40,000 is equal to 3,000 plus P, right? QZ, which is equal to 320 times 10 to the power minus 6 divided by IZZ, which is equal to 53.333 times 10 to the power minus 6, right? So with this, we can solve for P, right? So therefore, P will be equal, so 40,000 times by 53.333 power minus 6 divided by 320 power minus 6 equal minus by 3,000. So it's equal to 3. I got 3.667 times 10 to the power 3 Newton. Okay. So if we look at the answer, I wonder what's the answer now. If we look at the answer, yeah, it's 3. I mean, they round it off to 2 decimal places there. So we got 3 point. But this is not enough, okay? You have to, the next one, you have to check the failure mode number 2. So in exams, you or tests or the quiz, you have to check, okay? Why you have to check? Because this value is given, right? This value is given, okay? You cannot make the assumption, hey, Eugene always say that the failure will be at the joint. It's true, don't get me wrong, but we have to show we are learning now, okay? So marks will be awarded for checking also. That's important to know, okay? So next, mode 2 failure. So for mode 2 failure, it is failure of the wooden structure due to shear. Okay, due to shear. So the shear allowable, right, will be equal to what? The shear allowable for our case is equal to, where was it? 3 times 10 to the power 6. Okay. Right. So we know, I'm going to copy this diagram again. Right. We know that the maximum shear, oh, we ran out of page. It's okay. Is at the centroid. Right. So we know that tau max will occur at the centroid, right? So the formula to use, right, is equal to tau max is equal to V y over IZZ, okay, Q max divided by T. So for this case, Vy is a function that we form, is P plus by 3000, I think. Yeah, 3000 plus P. IZZ we know, right? Q max we don't know yet. Okay, then we have to find T. So we know over here, note T, right, is equal to twice multiplied by 20 times 10 to the power minus 3. Because it's left and right, right? So this is equal to 40 times 10 to the power minus 3 meters. Okay, so that's what we know. I'm going to go into another page. There's not enough page for this. Okay. I was being ambitious, thinking that I can do this example, but maybe not. But let's do. Right. So now the next thing we're going to do is we're going to calculate what is our Q max. And I'm going to show you 2 ways of calculating, and the answer will be exactly the same. Right. So this is the centroid. We know the distance from here to here is 60, right? So we can consider the top or the bottom, you decide. Okay. So let's do with the top first. Okay. So we're going to find Q max from the top. Q max from the top is a bit more work, okay, but let's do it. Okay. So Q max from the top is equal to Q of the flange, which we have already, plus by twice Q of the web, right? So Q of the flange we calculate earlier, it is equal to 320 times 10 to the power minus 6, okay, or 320 times 10 to the power 3. Okay, so 320, right, plus by twice. So the width is 20. The depth is 60, right? Right, because the first moment of area cannot cross the centroid, remember? Right, so multiply by 60 divided by 2. So this will come out to be 320 power 3 plus by 2 times 20 times 60 times 30 is equal to 392 times 10 to the power 3 millimeter cube. Okay, I'll go and do it again twice. 20 times by 60 times by 30. Okay, plus by 320 power 3 392. Okay, or 392 times 10 to the power minus 6 meter cube. Okay, so we can also find Q max. I'll see. Yeah, I'll do left and right. Okay, Q max from the bottom. Right. So Q max is equal to twice. So I'm looking at the bottom now, right? So the width is 20. The depth is 200 minus 60 multiplied by 200 minus 60, the whole thing divided by 2. Okay. So the answer should be the same. Okay, so 140 divided by 2 times by 140 times by 20 times 2 is equal to 392 times 10 to the power 3 millimeter cube, or 392 times 10 to the power minus 6 meter cube. Right, so you can see for yourself, right? Taking from the top or from the bottom, the answer will be exactly the same. I would rather do from the bottom, because the bottom, if you have not calculated the flange yet, right, it will take a longer time, yes or no? But because we calculate the flange, we know it's 320. If you don't know it's 320, you have to calculate. So the bottom part means this area. Okay, so it's just one thing to consider. Okay, so from here we know that the maximum shear, you can just plug in the formula, 3 times 10 to the power 3. Okay, so this is 3000 plus P, right? And then the first moment of area is 392 times 10 to the power minus 6, and then divide by the second moment of area, which is equal to, sorry, I need to look at 53.333 times 10 to the power minus 6, and then we are given the thickness. We calculated the thickness, which is equal to 40 times 10 to the power minus 3. So with this, P will be equal to 3 power 3 times by 3.333 power minus 6 times by 40 power minus 3, divide by 392 power minus 6, then minus by, oh, hold on, I did something wrong, 53.333 power minus 6 times by 40 power minus 3, divide by 392 power minus 6. Okay. Is this 3 times 10 to the power 3? I probably got it wrong. Hold on. Cannot be so. 3 power 6. Sorry, got it wrong. So 3 times 10 to the power 6. No wonder my numbers look so weird. 333 power minus 6 divided by 40 power minus 3 divided by 392 power minus 6. And then I'm going to minus 3 power 6 times by 3.333 power minus 6 times by 40 power 3 by 392 power minus 6. Okay, then minus by 3000, so I get 13326. Okay, 13326 times 10 to the power 3. right? So this is for mode 2 failure. So this is amount of force to fracture the wood, right? So which is much higher. So from here, we know that the P allowable, you have to pick the lower one. And it is the one that we calculate for the fastener, which is equal to 3.667. Okay, 3.667 Newton, and this is failure due to the nails. Okay, so it's not that bad. Okay, it's failure analysis, right? In the sense that we know that failure will occur either at the joints, okay, or if the joints is strong enough, right, it will fail at the what? At the centroid. But for our case, the joint fail first. That's why we pick 3.667 times 10 to the power 3. Okay, so if that's the case, I'm going to end my tutorial now. Okay, thank you for your time. I'm going to post a solution tomorrow. Okay, so I will still stay around if you have any other questions. Okay, thank you.